Hello, chemists. We are going to be going through some specific examples of calculating equilibrium constants and calculating concentrations from them using K sub S today. We learned basically what it was last time, and now we're going to learn how to do it pretty specifically. Apologies in advance if you hear kind of construction noises. They're doing something in the neighbor's house, don't know what. So there's basically two types of K sub S problems you're going to run to, and they are generally called AB type and A2B or AB2 types. A2B and AB2 are functionally the same as each other, so use whichever one is relevant. AB is a little bit simpler, so we'll run through that first. It's called AB type because we've got this here. If we've got a solid that dissolves, it's got two parts, an ionic solid with two parts, an A and a B. They can be anything as long as they are ionic, and they dissolve into a positive ion and a negative ion. So far, so review. The K sub S equation for that is concentration of A times concentration of B. As for Y, please refer to last video. To consider a specific example, silver chloride, and a specific problem, calculate the solubility product if the solubility of silver chloride at 25 degrees C is 1.35 times 10 to the negative fifth moles per liter. Now we got to do some math with it. They tell you the temperature because K sub S and K sub C change with different temperatures. So they just tell you the temperature so you know that the temperature is not changing. You don't have to do anything with that number yet. But the reason they tell it to you is so that you know that the K sub S is not going to change. So we look at concentration. We know the concentration of silver is going to be the same as the concentration of chlorine because for every mole of silver, we're going to have the same number of moles of chlorine. So 1 to 1, 2 to 2, 3 to 3, whatever. So we know that the concentration of, and we know that the concentration of each of those is equal to the concentration of silver chloride put together, because for every 1 mole of silver chloride, we have 1 mole of silver and 1 mole of chloride. So we know that the concentration of silver and chloride is both 1.35 times 10 to the negative fifth moles per liter. Since they're the same as each other, in order to calculate K sub S using this equation here, you don't need to do one times the other, although you can. What you can instead do is square it. So K sub S equals 1.35 times 10 to the negative fifth squared, because it's got the same number times itself. That's what we call squaring. So K sub S in this case is going to be 1.8 times 10 to the negative 10th. That number is quite small, which should tell you something interesting. All right. A little bit more complicated one. A saturated solution of silver chloride. They tell you saturated solution. As soon as you see saturated solution, you should know I'm dealing with a K sub S. Has a concentration of 1.46 times 10 to the negative third grams per liter at 18 degrees C. What is the solubility product of silver chloride at that temperature? And they give you the molar mass of silver chloride as well. First thing I want to point out is that this is in the wrong units, grams per liter. We want moles per liter. Luckily, they give you grams per mole. So we convert from one to the other. We convert from grams per liter to grams per mole, and we get this number for moles per liter, 1.02 times 10 to the negative fifth. You can do this equation in multiple steps if you like. If you want, I can make another video going through those steps as well, but this is a single step way to do it. Okay, so we get that number there for the moles per liter, 1.02 times 10 to the negative fifth. That's the unit you want, moles per liter. And at equilibrium, that's the equation there. AgCl solid is in equilibrium with silver and chlorine. So for each mole of silver chloride that dissolves 1 mole of silver ions and 1 mole of chlorine ions, that's what we said before. So they must be present in equal concentrations. So basically it's the same math we were doing just a second ago. We just had to convert from grams per liter to moles per liter first, which we do like this. Silver, 1.02 times 10 to the negative fifth. Chlorine, also 1.02 times 10 to the negative fifth. K sub S equals 1.02 times 10 to the negative fifth squared. Just like that. Cool. Now let's talk about A2B or AB2. Oh, sorry. There's a way to simplify that equation. Instead of saying K sub S equals concentration of A times concentration of B, we can use a unit called S. S just means the solubility of whatever you're talking about. Since they're all the same, we can just make that be one unit. It's usually called S. So K sub S equals S times S, solubility of one times the solubility of the other, which is the same, which is equal to S squared. And conversely, if we rearrange that, we can get S equals the square root of K sub S. So you can go from K sub S to S and back pretty easily. All right, now we're talking about A2B, or AB2 ionic solids. The only difference is that whichever one of the solid has a coefficient, or sorry, has a different number of ions, you're going to have a coefficient in the product side. And our equation looks like this: K sub S equals concentration of A squared times concentration of B. So consider this specific example: silver sulfide, Ag2S. We want to calculate the solubility product, that's K sub S, if the solubility of Ag2S at 25 degrees C is 1.16 times 10 to the 17th moles per liter. So that is the correct unit. We don't need to do any conversions with that. And it is solubility, which is our S unit, which we'll come to in a minute. So here is the generalized equation, kind of. We know that whatever the concentration of silver is, the concentration of sulfur is going to be half that, because we have 2 silvers for every 1 sulfur. So we have to multiply the sulfur by 2 in order to get the same concentration as silver, which is what they've done here. And the concentration of sulfur is going to be the same as the concentration of Ag2S, because for every mole of A2B, we have 1 mole of B. 2 moles of A, but 1 mole of B. All right, so the concentration of silver in this case is double the concentration of Ag2S. So that gives us 2.32 times 10 to the negative 17th, because we've doubled that. And K sub S equals this here, concentration of silver squared times concentration of sulfur. So we plug in our numbers there, our concentration of silver, that which we just calculated, our concentration of sulfur, which is the same as this, and plug and chug, get our number there, 6.2 times 10 to the negative 51. Whoa, that's fine. Sometimes you get really, really, really small numbers. Again, if you have a small number, it should tell you something. Do we have a unit here? Pause for effect. No, we don't. No unit. Okay, and you can go the other way as well. So if you, you can make a generalized form of this. If you've got this equation here, B negative 2 aqueous equals X moles per liter, and A positive aqueous equals 2X moles per liter. That's basically what we just did on the previous page. You put it in a similar formula to the one we did on the other page. K sub S equals 2S squared times S. K sub S equals 4S cubed, and rearrange that, S equals cube root of Ks over 4. I know it seems like we're using this 2 twice. Yep, we do. That's fine. That's just the way the equation works. Don't worry about it. That's it. Sorry, this video went a little bit long. Hopefully, having some specific examples will be helpful. See you soon.